Today we've got a really nice limit problem that comes from the problem section of the American Mathematical Monthly. So the specific problem number is E2961. So our goal here is to find all positive real numbers, we'll call them A, B, and C, such that the limit as n goes to infinity of the nth root of A plus B over C, all raised to the n power, exists and is finite. Okay, well, let's maybe do a little exploration first to come up with a guess. It's always good to have a guess and prove a guess rather than just go at it blind. Okay, so let's notice the following, like, pretty well-known fact. So since A is bigger than 0, we know the nth root of A tends to 1 as n tends to infinity. So I think that's pretty well known, and you can check that pretty easily using elementary limit techniques. So what does that mean? Well, that means if we take this limit as n goes to infinity of the nth root of A plus B, in other words, the numerator here, we get the number B plus 1. Okay, so what does that tell us? Well, in very loose terms, that means for what I'll call large values of n, well, for large values of n, this nth root of A plus B is essentially the same thing as B plus 1. But for large values of n, the whole thing, this nth root of A plus B over C to the n power looks like, so I'll just put a squiggle there to mean looks like, B plus 1 over C raised to the n power. Okay, so well, that's nice because it's pretty easy to calculate the limiting behavior of just a number raised to the nth power. In fact, I think it's pretty well known that this tends to 1 as n tends to infinity, and that is if B plus 1 over C is equal to 1. Well, that's just because we get 1 to the n. This will tend to 0 if B plus 1 over C is less than 1, and this will tend to infinity if B plus 1 over C is bigger than 1. That's because we'll, in this case, have a number that is less than 1 raised to the n power, and over here we'll have a number that is bigger than 1 raised to the n power. So, well, this doesn't really tell us what the limit should be, but it definitely sets up some sort of guess. And the guess would be something like this. So if we have B plus 1 over C, let's see, less than or equal to 1, which is the same thing as saying that B plus 1 is less than or equal to C, then it converges. And, well, that's because that corresponds to this case for large n, where we get a limit of 1 or a limit of 0. And I guess I should say converges and is finite, because that's our goal here. And then maybe the second case is if B plus 1 is bigger than or equal to C, then it diverges. And when I say diverges, then it diverges infinitely. But of course, this is just a guess, but I mean, it's a guess based on some pretty reasonable assumptions here. So that means that we've probably set up something that is provable, like a provable claim. So let's maybe state this as an official claim and see if we can prove it. So based on what is essentially a scratch calculation, we came up with the following conjecture for this question over here, and that is that this limit converges and is finite if and only if C is bigger than or equal to B plus 1. So that's a little bit different than the language that we had on the last board, but it's equivalent. So now we're going to break this into 3 cases. And the first case will be the case when C is equal to B plus 1. That's kind of a special case on its own. We saw that when we wrote out that triple of the limiting values there. Okay, so let's see how we might do this. So in this case, our limit turns into the following. So we've got this nth root of a plus b over b plus 1, and then this is all raised to the n power. But like we remarked before, the inside of this maybe exponent here is approaching 1 as n is approaching infinity. That's pretty clear because this nth root of a is approaching 1. We get b plus 1 over b plus 1. But then that means that this whole thing is kind of an indeterminate form of type 1 to the infinity. That's because we have n approaching infinity right here. And again, that's an indeterminate form. So in the case where we don't have a limit inside of the parentheses, it's not an indeterminate form. We just have 1 to the n, which is always equal to 1. But here the limit could really be anything. Okay, so now how do we tackle these exponential type indeterminate forms? Well, if you remember from calculus, the standard way to do this is to set this equal to L, some limit, and then we can apply L'Hopital's rule after taking the log. Okay, so let's take the log of both sides and see what we get. So this gives us the natural log of L, the limit, is equal to this limit as n approaches infinity of, well, now we're going to have n times the natural log of the nth root of a plus b minus the natural log of b plus 1. And there, I've used some logarithm rules there, but I think that's okay. Okay, but now what type of indeterminate form do we have? Well, now we have an indeterminate form of type, well, this is approaching infinity. So that's approaching infinity, and this stuff inside of the parentheses is approaching 0. That's because, well, they're both essentially approaching natural log of b plus 1. Well, one of them is already natural log of b plus 1. And so that's, again, not really exactly the type of format that we need for L'Hopital's rule. We'd need infinity over infinity or 0 over 0. But we can take care of that by taking this n and putting it as a 1 over n in the denominator. Okay, that's nice. And now we can apply L'Hopital's rule by taking the derivative of the numerator as well as the denominator. So we have the limit as n goes to infinity. And then let's see, in the denominator we'll have this minus 1 over n squared. That's the derivative of 1 over n. And then we're going to have some other stuff in the denominator as well. So notice that taking the derivative of the natural log of b plus 1, that'll give us 0. We have to be careful here because the variable that we're taking the derivative with respect to is n. Okay, so again, this goes to 0, but taking the derivative of this natural log will send the argument to the denominator. So we've got this nth root of a plus b in the denominator. And then we have to take the derivative of the inside. But the derivative of the inside is a little bit tricky, but if you remember the chain rule as well as the general formula for derivatives of exponentials, it shouldn't be too bad. So this is going to give us something like this. Minus 1 over n squared times the natural log of a times a to the 1 over n. So again, this 1 over n squared comes from taking the derivative of the 1 over n in the exponent, and then the natural log of a times a to the 1 over n is from the general exponential rule. But now we get some simplification here. So notice that this 1 over n squared and this 1 over n squared, along with the minus sign, cancel each other. And then we no longer have an indeterminate form. So as we discussed before, this a to the 1 over n will simply approach the number 1. And then this nth root of a, which is also a to the 1 over n, will also approach 1. So putting this all together, we'll have the natural log of a over b plus 1. But then that's going to be the natural log of a to the power 1 over b plus 1. But that's the natural log of our limit. We can exponentiate both sides, and we'll get L is equal to a to the 1 over b plus 1. Okay, so there we have a value of our limit in the case when c is equal to b plus 1. Now let's move on to the other two cases. So in our first case, when c was equal to b plus 1, we got a limit, and that limit was a to the 1 over c or a to the 1 over b plus 1. And now we're moving on to our next case when c is bigger than b plus 1. And from our guess before, we expect the limit here to be 0. And also notice that's one of the cases here where we have the limit converges and is finite. Okay, so let's start with the following observations, which, we've made some of these before, but I think it's okay to make them again. The limit as n goes to infinity of the nth root of a is going to approach 1, but that means that the limit as n goes to infinity of the nth root of a plus b is going to approach b plus 1, but then the limit as n goes to infinity of the nth root of a plus b over c will be less than 1. Well, it's actually equal to b plus 1 over c, which is less than 1. But now we're going to use the precise definition of the limit. So let's recall that for all epsilon bigger than 0, there exists some capital N, which is a natural number, such that if little n is bigger than or equal to capital N, we have this nth root of a plus b over c minus b plus 1 over c is less than epsilon. So in other words, the term that we have right here, the thing that we're finding the limit of, is within epsilon of our limit. But now what I'll do is I'll take a number x, and I'll take that x to be half the distance between 1 and b plus 1 over c. So let's say that will be 1/2 1 minus b plus 1 over c. And notice that's going to be a positive number that's between 0 and 1, pretty clearly just based on like where all of these numbers kind of naturally lie. And then let's also let n naught, or maybe I'll say n sub x, be the, I'll say it, corresponding value of n in this case, related to the precise definition of the limit right there. Okay, so what does that tell us? Well, that tells us for all lowercase n bigger than n sub x, we have the nth root of a plus b over c lives in this little spot on the number line, which I'll just like write out here. So let's maybe put the number 0 back here. We'll put the number 1 right here. Here is the number 1 minus x. And then that's all we're going to put on the number line. And what I'll say is that by this line right here, we have all of these numbers right here live on this side of 1 minus x. Now we could bound this below by something, but we don't really need to bound it below by something. Okay, so that means what? So that means that we have the nth root of a plus b over c raised to the n power is strictly less than 1 minus x to the n power. But notice 1 minus x is a number between 0 and 1. So when we take that to the nth power and then take the limit, that's going to go off towards 0. But then on the other hand, this is a positive number, so that we've bound that above as well. So by the squeeze theorem, we know that the limit of this term is also equal to 0. Okay, so now let's move on to our third case. Okay, so for our last case, we'll look at the case when c is less than b plus 1. And the argument here is really similar to the argument in case 2, so I'll let you fill in some of the details that we skip. So let's notice that in this case, we have the limit as n goes to infinity of the nth root of a plus b over c will be bigger than 1. Again, that's because c is less than b plus 1, so our numerator is larger than our denominator. This actually tends to b plus 1 over c again, but again, by that inequality, that is larger than 1. Okay, so that means that we can find an x bigger than 0 and an n, which is a natural number, such that if lowercase n is bigger than capital N, we have the nth root of a plus b over c is bigger than 1 plus x. Well, that's because this limit is bigger than 1. And well, what could this x be? Well, I guess you could take it like halfway in between the actual limit and the number 1. So you can bound it like away from 1 by some certain distance. Okay, so next up, let's take this to the nth power. And we'll take this to the nth power as well. And the inequality keeps going in the correct direction. But now let's apply a well-known inequality to say that this is bigger than 1 plus n times x. But then, since x is bigger than 0, well, if we take n to infinity, this is going to pretty clearly go to infinity. But we've got our term is larger than something that goes to infinity, so that means its limit is infinity. So that wraps up case 3 and thus finishes proving this claim. So if you're still around and you liked the video, make sure to like the video. And if you haven't subscribed yet, maybe consider subscribing. It would really help us out. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.